Greetings and welcome back. In this section, we've got question 6 based on chemical equilibrium. The question reads as follows: 1 mole of pure hydrogen iodide gas, Hi, that is the chemical formula for hydrogen iodide, is sealed in a 1 cubic decimeter container at 721 Kelvin, that is the temperature. Equilibrium is reached according to the following balanced equation. So we are given the balanced equation here. 2Hi is equal to hydrogen plus iodine. It is found that 0.11 moles of iodine are present at equilibrium. So this is the number of moles of iodine present at equilibrium. State Chatelier's principle. So you always expect this question in the exam, because this question, Chatelier is the scientist who is involved with the studies on reactions that are at equilibrium. So the principle is stated as follows. When an equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will oppose the disturbance, or you can say by favoring a reaction that will counteract the disturbance. So I'll write it down here. So the principle reads as follows: when an equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will oppose or counteract the disturbance. We know that the conditions that are disturbed here, when we refer to a disturbance, means we may change the pressure of the system in relation to gases, or we can change the concentration of the system by adding maybe one of the reactants or removing the one of the products, and also we may change the temperature. So when one of these conditions is changed, or maybe two or more of them is changed, the system will find a new equilibrium by favoring a reaction that will oppose our disturbance. For example, when we increase the temperature, the system will find a new equilibrium by favoring a reaction that will lower the temperature or decrease the temperature. Then 6.2, determine the number of moles of each of the following at equilibrium. So we are given that 0.11 moles of iodine are present at equilibrium. So how many moles of hydrogen are present at equilibrium? So we find that hydrogen is one of the products, okay, and we are given that the number of moles of iodine is 0.11. So looking at the mole ratio, here we have got a 1, so the mole ratio is 1:1. So it means we have the same ratio of moles for iodine as we have for hydrogen. So meaning that the number of moles of iodine will be equal to the number of moles of hydrogen, because we have got the same ratio in our products, 1:1. Okay, so there is a 1 here, and 1 mole and 1 mole. So we have to write the answer as number of moles of hydrogen H2 is equal to 0.11 moles. So those are the number of moles for hydrogen, because of the ratio of the products is 1:1. Now then we are required to find the ratio of the number of moles of hydrogen iodide at equilibrium. Remember that we have 1 mole of hydrogen iodide at equilibrium, but some moles were used, and now we want to find how many of these do we have. Now, to explain this part, I know it's one part, but to explain this section here accurately or more clearly, we can draw up what we always refer to as a Rice table. Now, a Rice table is in RICEE. Okay, that is a mnemonic that teachers will always use to refer to this type of table. Now, I'll explain what that rice word relates to. So what we have in our table is we put in the formulae for our reactants here. So we've got hydrogen iodide, hydrogen and iodine. So we draw up our table here. So we have Hi, and then we always advise that you put a double line here to show a distinction between the reactants and the products. So on this side we have got the two products, which is hydrogen and iodine, like that. Now the ratio here, the R refers to the rate, the ratio of the moles, or the mole ratio. Now the mole ratio here, we have got 2 moles of hydrogen as in the balanced equation, and then you have got a 1, 1. Okay, so the R relates to the first row, is a row that is indicating the ratio. Sometimes it's not necessary to write that. You can just ignore it because you will find it in your balanced equation here. Now then I refers to the number of moles that are there initially, initial moles. So I is for initial number of moles. In other words, how many moles were there initially at the start of the reaction. C refers to the change in the number of moles. Change refers to how many moles were used up and how many moles were formed. So that's what the C relates to. And then we have the E. The first E refers to the number of moles at equilibrium moles. And then the second E is the equilibrium concentration. What is the concentration at equilibrium? So we have to draw up a table with 5 rows like that. We've got 5 rows. Okay, so here when we put in the information, we are given that 1 mole of pure hydrogen iodide is sealed in 1 cubic decimeter of a container. So it means here we have got 1 mole. So the initial number of moles for Hi is 1. And then we know that at the start of the reaction, there are no products, so there is no hydrogen and there is no iodine. So that's what we have here. And then at the end, we are given that at equilibrium, the number of moles is 0.11. So equilibrium here, at equilibrium, the number of moles is 0.11. That is for iodine. So it means here I've got 0.11 moles for iodine. Now, when we get this information here, which means now we can determine the change in our iodine. Remember, we had no iodine, no number of moles at the beginning. So it means if we now have 0.11 moles, so it means we formed 0.11 moles during the reaction. Now, this row here the rho of change, it is now determined using the ratio. So if we formed 0.11 number of moles, the ratio for iodine and hydrogen is 1:1. So it means here we also have 0.11. So these two, the change and the ratio, they must go hand in hand. Now if we formed 0.11 moles of hydrogen, how much was used up? Now according to the ratio, we have to multiply the number of moles here by 2. So this is 0.22. So we formed we actually used 0.22. That is 0.22 moles because of the mole ratio. Now remember, I'm just using this table to explain what is the number of moles that we need over here. So now the number of moles at equilibrium means that initially we had 1 mole. Now the change, it means we used 0.22 moles. Remember, Hi is a reactant. It's on the reactant side. It's reacting. So as it is reacting, it is being used up. So this has to subtract. So we have to subtract this. So in other words, we had 1 more initially. Now we used 0.22. Now how much do we have here? We have got 0.78 moles. And of course, for hydrogen, we have got 0.11 moles according to the ratio. Remember, we had no hydrogen. Now we formed, these ones are products, so we are forming them, so we add them here. So 0 plus 0.11 will now have 0.11 moles. So it means at equilibrium, we have 0.78 of hydrogen and 0.11 of, we have got 0.78 of hydrogen iodide, and we have got 0.11 moles of hydrogen and 0.11 moles of iodine. Now the concentration, this rho for concentration, we use it for calculating what is the concentration at equilibrium. So we use that formula, C is equal to NV, the number of moles at equilibrium divided by the volume. Now we are given that our V is 1 mole per cubic decimeter. So it means our concentration here is 0.78 divided by 1 over 1, which will give us the 0.78. And this one will be 0.11, and this is 0.11. Now, why am I explaining this? Because I wanted us to get clearer on, to clarify on what is the answer to that. So you realize that the number of moles of hydrogen iodide at equilibrium is this particular value that we get here, okay, which is 0.78. So to answer that question 6.22, we would say the number of moles of hydrogen iodide is 1 minus 0.22. We had 1 mole, we used 0.22, now we are going to have 0.78 moles at equilibrium. Okay, that's how we come to that answer there. You can answer that question, it's 1 mark, so you don't have to spend so much. You have to determine if we formed 0.11 moles of iodine, okay, according to the ratio here, how much did we use? So it means we use twice as much. So we used 0.22. So then we have to subtract that from 1 mole. And then we'll get the answer 0.78. Now let's come to the second question, 6.331. The equilibrium constant Kc at 721 Kelvin is 0.02. The temperature of the container is now increased to 850 Kelvin. The equilibrium constant Kc at 850 K is 0.09. Is the forward reaction exothermic or endothermic? Now here you'll find that we are now having a situation where we changed one of the conditions, and the conditions that we have changed here is temperature. Now temperature is the only condition or the only factor that can change the Kc, the equilibrium constant. Now the equilibrium constant is defined as the concentration of the products divided by the concentration of the reactants. Now I'll use this to explain the relevance of this formula in this particular situation. Now we are given that when the temperature was increased, the equilibrium constant also increased. So looking at this formula here, when the equilibrium constant changes, it means that the products have increased. We are actually increasing the products. So a change in the Kc implies that the reaction is a forward reaction. We are forming more products. In other words, the numerator here is increasing. So when we form more products, it means that we are favoring a forward reaction. We are favoring a forward reaction. Now in this case, the question is asking, is the forward reaction exothermic or endothermic? Now to analyze that question, 6.31 is part of what we have here now. So one, we can say that I see here in 632, they are asking us to explain the answer. So let's start by the explanation so that you will see how we can come to the answer to that. Now, if we come to the explanation 632, we'll find that an increase in temperature, what does that do? It favors an endothermic reaction. Now, this is based on the Chatelier's principle. Remember, we said that when an equilibrium in an isolated system is disturbed, the system will reinstate a new equilibrium by favoring a reaction that will oppose. So the opposing here is in the fact that when we increase the temperature, the system will favor an endothermic. What does an endothermic reaction do? It decreases a temperature. So the endothermic reaction has a tendency of reducing the surrounding temperature. So when we increase temperature, the system reduces temperature by favoring an endothermic reaction. So we now know that when we increase the temperature, the system favored an endothermic reaction. Now, this endothermic reaction, was it a forward or a reverse reaction? How do we know? Now we see that the Kc increased from 0.99 to 0.09. So it means we can say yes, one of our reason, the second part of the reason is that forward reaction and increase in temperature favored a forward reaction. How do we know that forward reaction was favored? Because the Kc, the equilibrium constant, was increased. Okay, it increased from 0.29. So we know that an increase in temperature favored a forward reaction. When a Kc increases, it implies that we formed more products. So when we form more products, it means our reaction is favoring forward. Now, by deduction, we can now see that if an increase in temperature favors endothermic, and that endothermic reaction is a forward reaction because a Kc increased. So we can go back here to 6.3.1 and say therefore our forward reaction was endothermic. So we favored an endothermic reaction that reduced a temperature, and by so doing our products increased. Okay, I hope you get that part there. So we have to work ourselves backward. You cannot just write exothermic or endothermic. You have to give the reasons. Okay, so and these are the reasons that we have here. An increase in temperature favored endothermic, and an increase in temperature favored a forward reaction because the Kc increased. Okay, so you can also say here that the Kc increased, therefore forward reaction is favored. So it means that forward reaction is our endothermic reaction, which is what they are asking us here. Is the forward reaction exothermic? So if the forward reaction is exothermic or endothermic, if the forward reaction is endothermic, it means the reverse reaction is exothermic. The last question, 6.33, calculate the mass of Hi present at the new equilibrium at 850 Kelvin. That is where the bulk of the marks are. Calculate the mass of hydrogen iodide present at the new equilibrium. Now, when you see these marks here, that's where usually you are advised or encouraged to draw up a table, that rice table. Here is compulsory to draw a rice table. A rice table will simplify our work. Now, so let's look at how we can work that one out. Now the rice table, coming back to our table, I've briefly explained what the rice table stands for. So now what we have here is to draw up again this table, bring this table down here. In the first question, it was not necessary to draw it as I explained earlier. So let's draw it now here. We have got hydrogen iodide, and then we have got our reactants, which are our products H2 and iodine I2 and I2. Okay, and then over here we have got our initial number of moles, and then we have got our change. I'm deliberately leaving out the ratio. The ratio, we know that here there is a 2, then there is a 1 and a 1. So you can read it from there. Okay, and then the change, so you've got the initial number of moles, and what is the change in the number of moles, and what is the number of moles at equilibrium moles, and then what is the concentration at equilibrium concentration. So those are the 5 rows that we have So we can draw up like that. Now, what do we have now here? We have, what now we have is, we are given that this is a new equilibrium, so we have to calculate the mass of HI at the new equilibrium. So this table that we drew up here, it was for the first equilibrium. Initially we had 1 mole, and then we reacted, and then at equilibrium we have got 0.7778 and 0.011. Now at the second reaction, or the second equilibrium, you will find that we had 0.78 moles of hydrogen iodide. So the number of moles that we have here at the end of the first reaction is going to be the initial number of moles in our reaction here. So initially, we are not going to start with 1 mole, but we are going to start with 0.78 number of moles. Okay, because remember, our first reaction occurred, and then we reached an equilibrium. Then we have got 0.788, 0.11, 0.11. Now we are going to start a new reaction at 850 kilokelvin. So now we are going to start with this number of moles here. So those number of moles are going to be our initial, because it's a second equilibrium. So we are going to have 0.11 and 0.11. I hope that you get that part. So now, and then we are not given how many number of moles we have used up, or how many moles we have at equilibrium. So they are just asking us to calculate the mass of HI. So we have to introduce our unknowns here. Now let's say I'm going to use an unknown. Let's say we formed X number of moles for hydrogen, which means we will also have X number of moles for iodine. And here we are going to use double as much. So I'm letting X being the change in my number of moles, because we are not given how many moles we used up, and neither are we given the number of moles of each at equilibrium. So let this be X, and this one will be 2X. Remember, according to the ratio. Once we have here X, the number of hydrogen iodide moles should be double, twice. Okay, you can let this one be X, but once you make it your X here, then this one should be half X and half X, which is not what we want. We don't want to work with the fractions for now, but it's another option that you can also take. So I'm just using X as whole numbers, so that here we've got 2X. Now, let's look at what will happen at equilibrium. So it means in the second reaction at 850 Kelvin, now we had 0.778. Now our change, it means we are using this. That's why we put a double line here, to make a distinction between what is being used up and what is being formed. Remember, when a reaction is used, the reactants are being used up. In other words, the quantities are getting less and less. And here on the right, the products are forming. So here, our change implies that we are separating. Here, our change implies that we are adding. So now we are saying we had 0.78 moles initially, and our change in terms of x is 2x. So how many moles do we have at equilibrium? So we have 0.78 minus 2x. Okay, we express that algebraically like that. And for hydrogen, we had 0.11, and our change means we added x moles. So we now have 0.11 plus x. Those are the number of moles. Here similarly 0.11 plus x, what we had initially plus what we formed. And then we are now going to have the equilibrium concentration. So what is our concentration? Remember, concentration is number of moles at equilibrium divided by V. That's why it's called the Kc, because it's a constant that is using concentration, the equilibrium constant. So we have to use the concentrations. So our concentration at equilibrium is going to be the number of moles at equilibrium, which is 0.78 minus 2x divided by 1 mole. Remember, our volume is 1 cubic decimeter. So divide by 1, which will keep this fraction the same, 0.78 minus 2x. And here we are going to divide again by 0.11 plus x, everything divided by 1. And this 0.11 plus x, everything divided by 1. So we now have our concentrations at equilibrium, which are these values here, that one, and that. Now that brings us now to the Kc. We are given that the Kc is 0.09. So the Kc is 0.09. So coming back to the formula, remember we said that the Kc is defined as the concentration of the products divided by the concentration of the reactants. Concentration of products over concentration of reactants. So let's substitute these values according to our table. So our Kc, we have been given, it is 0.09. It will be equal to concentration of our products. Our products, this is concentration of hydrogen by concentration of iodine over the concentration of hydrogen iodide. Hydrogen iodide is Hi, but now because of the coefficient 2, we have to square that. We square the Hi. Then we can now put in our values, which means 0.09 is equal to the concentration of H2. This is 0.11 plus x times 0.11 plus x over 0.78 minus 2x, that one squared because of that 2. So that's why we need those concentrations at equilibrium. Now we have to evaluate that. Now moving further, we are going to have here 0.09 is going to, you can write this one as 0.11 plus 11 squared, because it's multiplying itself there, over 0.78 minus 2x squared. Now the aim here is to calculate the x. Remember, the question is to calculate the mass of hydrogen iodide present at equilibrium. So we are looking for at equilibrium here, what is the mass of hydrogen iodide? What is the mass here of hydrogen iodide at equilibrium? So if we know the number of moles at equilibrium, for hydrogen iodide, then we can calculate the mass by using mass is equal to number of moles times molar mass. We can calculate that. Okay, remember the formula: N is equal to M over molar mass. That's what we have. So we are calculating the M. So the reason why we have to calculate the X, we need to know how much is this X, then subtract from 0.78 minus 2 times that value, and then when we get that number of moles, then we can calculate that. So we now need to solve that part. Now that is a rather complex formula or equation to solve, but what we can do is to possibly, let's combine this together. We are going to have here 0.09 is equal to, I'll write it as 0.11 plus x over 0.78 minus 2x. Everything is being squared. Everything is squared because this is the numerator is squared, the denominator is squared, so we can write this as 0.11 plus that squared. Now that can give us the leverage to take a square root on both sides, so we are going to take a square root. So I'm going to have here 0.11 plus x over 0.78 minus 2x is going to be the square root of 0.9, that is 0.3, I guess 0.3. Let's put it in a calculator here. Root of 0.09, yeah, that is 3 over 10, which is 0.3. So now let's take this one over, maybe let's put it here somewhere there. We can now say therefore multiply by 0.3, remove the denominator here, so I'm going to have 0.3 by 0.78 minus 2x is equal to 0.11x. Okay, and then multiply that one out. Okay, let's just take out and let's just put it here. Take out this one. Okay, so we now have here 0.11 plus x, and then we now have here multiply 0.3 by that one. Okay, let's see, what is 0.3 multiplied by 0.78. This gives us 0.234. Okay, so what is 0.234 multiply that one minus 0.6x is equal to 0.11 plus x. Now collecting like terms, this one subtract, this one comes here, so I'm going to have 0.124 is going to give me 1.6x, because this one will add and this one will subtract. Okay, then divide by 1.6 divided by 1.6. So therefore our x this side is going to give us 0.124 by 1.6. Okay, 0.124 and that's a 24. Okay, 24.124 divided by 1.6. Answer is 0.0775. So this is 0.0775. So that is the value of x. Now let us now calculate the number of moles of hydrogen iodide at equilibrium how much is it going to be? It is going to be 0.78 minus 2 by 0.0775. Okay, remember what we have here. At equilibrium, the number of moles of Hi is 0.78 minus 2 by the value of x, which we have just calculated now. So we now have that, and let us calculate that. This is 0.78 0.78 minus 2 by 0.0775. Okay, I've got 3 sevens there, and I still need 775. Okay, that is correct. Equals, we'll get 5 over 8, and let's just express it in decimal, 0.625. So this is equal to 0.625 number of moles. Therefore, what is the mass of Hi? Therefore, the mass of Hi is going to be 0.625 multiplied by the molar mass of hydrogen iodide. Now, from the periodic table, we are able to find the molar mass. We have got H and I. H, the molar mass there is 1, that is the relative atomic mass. So take the 1 plus the I, the iodine. The iodine is here, is 127. So when we add those two, 127 plus 1, we are going to get 128. So we will multiply that by 128. So it's 0.625 multiplied by 128, which is the molar mass for hydrogen iodide. And then we will get 0.625. I still have the number here, multiplied by 128 to 8. That is 80, and that is 80. So that 80 is 80 grams. So therefore, the mass of the hydrogen iodide at equilibrium is 80 grams. Okay, that was a lengthy calculation with 8 marks, but I hope you get something from here. So we have come to the end of this tutorial. Please share it, like it. If you have got any questions, just drop your comments or questions in the comment section. Also remember to subscribe, to like, and to share, so that when I post new videos, you'll be notified of new content that I'll be loading. Otherwise, have a wonderful time. See you next time.